All right, Chemistry 3101. This is where we left off. Last class was finishing up section 10.7. We're going to skip sections 10.8 and 10.9, so I'll scribble that in here. Skip 10.8 and 10.9. I'm not saying they're not interesting. They're just not covered on the final exam, and so you don't need to worry about those. I've also never seen any content from those sections on any kind of standardized exam, an MCAT or a DAT or anything like that. So you can look at that as an FYI. And now we're going to talk about the second to last section that we cover, which is radical addition of HBr across a double bond. And this goes all the way back to chapter 8. It says here chapter 9. That's a typo. It should say chapter 8. Let's fix that up. So way back in chapter 8, the alkenes chapter, we learned that if you add HX, whether it's HCl or HBr across a double bond, you get Markovnikov addition, right? The rich get richer. So if we look at this compound here, this is called isobutylene. We have two hydrogens on this carbon here. I'll highlight that carbon in red, let's say, and I'll highlight this carbon in blue. Well, the rich get richer, so the carbon that's in red is the one that's going to take the proton from the HBr, and the carbon in blue is the one that's going to take the bromine from my HBr. So Markovnikov addition. Now, when we were in chapter 8, I didn't go over the whole history of how it was discovered that peroxides were required to affect an anti-Markovnikov addition across a double bond. But basically what scientists found was that they were getting mixtures of Markovnikov and anti-Markovnikov. And they said, well, why are we getting mixtures sometimes? Other times we get completely Markovnikov. Other times we get completely anti-Markovnikov. They thought it could even be related to the phases of the moon, which we laugh at now. But what they found out was that there was an impurity in the solvent that was leading to the anti-Markovnikov. In some solvents, if you let them sit in the presence of light for long enough, they will form organic peroxides, what I have in this yellow circle here. So the organic peroxides are what was causing the anti-Markovnikov addition. So they uncovered that. And what we're going to talk about today is the mechanism of this reaction. Back in chapter 8, all I taught you was this. I said, you just need to know this. If you throw some peroxides in with your HBr and your alkene, you get anti-Markovnikov. The bromine goes to the less substituted carbon, and the hydrogen goes to the more substituted carbon. So now we're going to uncover why specifically does that happen, and we aren't able to do that until we study radicals, which we're doing in this chapter. So now we can rationalize the formation of the anti-Markovnikov product. Well, let's get into it. It says here that the reaction is actually initiated by the thermal homolysis, which just means the heat breaking of the peroxide, which makes a radical and forms a bromine radical from HBr. So the first thing, remember that we have a mixture of course, our HBr and our organic peroxides. So when we heat that up, what happens is you cleave the bond between the two oxygens and you make a pair of radicals. And one of those radicals, or any one of those radicals, could react with a molecule of HBr to produce an alcohol, but you end up forming a bromine radical. Now, not every single molecule of HBr is going to be converted into a bromine radical. Some of them will be converted into bromine radicals, but we're still going to have HBr in our reaction mixture. So now that you've made a radical, a bromine radical, here comes the key step. This is like the magician revealing his secret in a way. Me showing you, this is how it happens. Check it out. If you have the bromine radical and your alkene, you've got two possibilities for the bromine, right? You've got two carbons in the double bond. It could either add to the red carbon. That would occur like this. So you'd form a bond between the red carbon and the bromine, and then you'd put the radical here. That would give you a tertiary radical. The bromine is adding at the less substituted position. However, you could also add the bromine at the more substituted carbon. The thing is, when we do that, there's nothing technically wrong with that. Let me just draw that a little better. There we go, like this. But we end up with a secondary radical. What's the difference between a tertiary and a secondary radical? Well, you can clearly see from the notes here that a tertiary radical is more stable and it's going to be favored. So that is why the bromine adds to the less substituted carbon. It's based on the exact same thing that the addition of HBr across a double bond. It's based on the same rationale. It's about forming the most stable intermediate. Before we were forming the most stable carbocation. Now we're forming the most stable radical. So the whole thing is based on forming the lower energy intermediate, the most stable radical, which is going to be produced via a lower energy transition state. And that's the answer to the entire thing like that. So the bromine adds to the less substituted carbon. This is the rule, because you produce the most stable radical. Once the bromine adds, you end up with that tertiary radical in this case. Then you abstract a proton from HBr. Remember, I was careful to say that not every single molecule of HBr is converted into a bromine radical. Some of them are, but the radical that's produced as an intermediate abstracts a proton from the HBr, and there you go. There's your anti-Markovnikov product, and that's the reason why you form the anti-Markovnikov product. Now, what about the termination? Yesterday, we talked about initiation, propagation, and termination. Well, in this reaction, hopefully you noticed that the only radical that we had in there was a bromine radical. There was no methyl radicals or anything else. So at any moment in time, most of the radicals are going to be bromine radicals. You could, theoretically, you could have this as a radical too. But anyhow, any two radicals coming together count as a termination step. But again, the radical that's going to be present in the greatest amount would be the bromine radicals. Two of them come together and make a Br2 molecule, and that annihilates your radicals or destroys them, okay? Anyhow, but the bottom line is, like I just said, I'm repeating myself, the combination of any two radicals counts, okay? Any two radicals coming together, that counts as a termination step, and that's the entire mechanism right there, the whole thing. Now, in terms of the addition of HBr, if we look at the delta G for the addition of HBr with peroxides across the double bond, it's a spontaneous reaction. So the delta G is going to be negative. However, if you're wondering, well, why can't you do it with HCl and HI? It's because both of those, the overall process is thermodynamically unfavored, okay? The delta G is going to be positive in both of those cases. Now, our book, not in my slides, but in the textbook, they go into a full treatment of looking at the addition step and the hydrogen abstraction step for HCl and HI, and they go through, that, the addition step, it's thermodynamically disfavored for HI, but it's favored for HCl and HBr. Then so HI just won't work. And then you go down here and it says for the hydrogen abstraction, HCl is not thermodynamically favored. So the only one that works is HBr. I didn't put that in my slides. I'll let you take a look at that on your own time. So you might want to read that section. It's not long. It's like, 10 lines or something. So we'll put here, read this part about thermodynamics. Again, it's not very long, but it provides more background on why we only add HBr. You're never going to see this in organic chemistry. You'll never see HCl in peroxides. And you're never going to see HI in peroxides. That's not going to happen. Okay, only HBr and peroxides. Now, what about the stereochemistry of this addition? I know students sometimes will roll their eyes when they think about, when they hear the word stereochemistry, but bear with me. I don't think it's that complex, because what happens is that we end up forming a carbon radical, and we talked about the molecular geometry of carbon radicals yesterday. We said, okay, well, if you have the bromine, okay, radical, and it adds at the most substituted carbon, like this, I think that by now everybody knows that when you end up with this radical, okay, that this is treated as if it's trigonal planar. So that means the hydrogen abstraction can occur from either side, and all that doesn't even produce a stereocenter. But as far as the addition of the bromine to this carbon, since this carbon is sp2, it's also trigonal planar. trigonal planar. And thus, it could attack from either face of the molecule. And so you could end up with a racemic, or you would end up with a racemic mixture in this case. If you already had a stereocenter in the molecule, well, in that case, it would be a little bit different. You'd end up with a pair of diastereomers, but that's not what we're seeing on this slide. That would be a different case. All right, let's try some practice problems here. Stereochemistry comes into play here a little bit. It says, predict the products for each reaction. In each case, be sure to consider whether a chirality center is being generated, and then draw every stereoisomer that you could obtain. Well, we're not going to draw the whole mechanism. It doesn't ask us to draw any mechanism at all here, but I always think it's fun to give it the old college try. So why don't we start with our bromine radical? And what I'm going to do is I'm going to label this carbon in red and this carbon in blue. Could anybody tell me which carbon is the bromine going to attach to? Will it attach to the red carbon or the blue carbon? And it's not a question to try to fool you. I'm just getting a sense here, or letting you give it a shot. Absolutely, right? Because it's anti-Markovnikov. You're both 100% correct. Okay, so let me just erase those for the sake of simplicity. So what's going to happen is we're going to form a bond between the bromine and the carbon at the end, and we're going to form the most stable radical. So let's draw that radical intermediate just for fun. So we end up with 1, 2, 3, 4, like this. We end up with this radical. But, oops, I didn't even put my bromine in there. That's not right. There we go. I was forgetting something. There we go. So we form the most stable radical. This is a tertiary radical. Now, this is not a stereocenter where I have the circle. It's not a stereocenter because that carbon is already attached to 2 hydrogens. Ergo, it doesn't have 4 unique groups. We can remove those. However, when the hydrogen abstraction takes place from the HBr, here I am going to form a stereocenter, and I can add the hydrogen to either face of the molecule. So I can add it like this. So I'm kind of running out of space here, but I say that every day. Anyhow, so I could end up with the hydrogen in the back, and I can end up with the hydrogen in the front. Either one. Okay, and I didn't draw the hydrogen in, obviously, because this is a bond line structure, but we end up with a pair of enantiomers. So I'll just scribble that in here, enantiomers. What about the next one? Could anybody tell me how many products I would get from B? Is anybody able to just look at that and say, you'd get 1, 2, 3, 4, I don't know. How many different products you could get from this one? How many products would you get from this second one? Do you think it would be 1 or 2 or 3? Would you form a stereocenter? Yeah, absolutely. Yeah. So what I'm seeing in the chat is my students are saying only 1 product, and I think they're perfectly correct because you don't form a stereocenter here, do you? The bromine is going to add to the less substituted carbon to make the more substituted radical intermediate. Let's draw that. It's going to look like this. So we have the bromine over here. We have our radical here. And we can see that this is not a stereocenter where I have the yellow highlighter. And when I add a proton here in the next step, that's not a stereocenter either. So I'm only going to form one product. So let's draw, oops, that's not what I wanted to do. There we go. So we're only going to form one product, and that is going to be this compound. So we'll put here no chiral centers. None. Zip. No chiral centers whatsoever in this molecule. So we only get one product. And that, my friends, is it for new material in Organic Chemistry 1. You have covered all of the new material that there is in this class. We don't cover sections 10.11 or 10.12. I just want to double check to make sure I have the right numbers. Just kidding. So yeah, we don't cover, we're going to skip 10.11 and 10.12, and we're going to move right to section 10.13, in which there's no new information. It's just rehashing some of the things that we've looked at and discussing, the synthetic utility of halogenation. Why did we learn about halogenation of alkanes? We spent a lot of time talking about it yesterday. Well, first of all, if you have an alkane, there's really nothing else you can do except to functionalize it with a halogen to make an alkyl halide. But the thing is, if you go back to chapter 7, we learned a million things that you could do with an alkyl halide, right? We learned substitution reactions and elimination reactions. Now, the two types of halogenation that we know work are chlorination and bromination. Bromination is more useful because it's more selective. However, chlorination can be useful if you have something that's symmetrical. If you have a substrate that's highly symmetrical, sure, you can do chlorination because there's only one possible product that can be formed. However, if you have a compound like this, 3-methylpentane, when that undergoes bromination, it's only going to occur, it's vastly going to occur at the most substituted position. And so we get a very high yield of 3-bromo, 3-methylpentane. And then what can we do with that? We can do all kinds of substitution and elimination reactions. We could make the Zaitsev alkene, we could make the Hoffman alkene. And then once you have an alkene, the world becomes your oyster. So this is what I showed you yesterday. The whole point of halogenation is functionalizing something that has no functional group. That's really all there is. So every time in this class, if I ever give you an alkane as a starting material, the only possibility you have is to halogenate it. That is it. Okay, there's nothing else you can do. So if it's unsymmetrical or asymmetrical, you want to do bromination. If it's completely symmetrical, you can do chlorination if you want. I'll be honest with you. Most of my students just stick with bromination. They seem to like that the most, and there's no problem with that at all. In fact, if I had to deal with bromine or chlorine, I would pick bromine because bromine is a liquid at room temperature, whereas chlorine is a gas. And I don't want to mess around with a gas, and you have to get a regulator and all this stuff to dish out a gas. That doesn't sound fun to me whatsoever. So once you functionalize the alkane as an alkyl halide, then it's open to substitution and elimination, SN1, SN2, E1, E2. And then if you do an elimination and you make an alkene, whoa, then you really open up the floodgates, right? You can do all kinds of stuff. You can make a geminal or vicinal dihalide. You can make an alkyne. You can do, the addition of, water across there. There's so many different things that you can do with a double bond. So it really opens up a wide range of possibilities. Well, that's the end of chapter 13, and this is just a quick review of the reactions that we looked at. Today, we discussed the mechanism of anti-Markovnikov of HBr across an alkene, and we explained why the bromine goes to the less substituted carbon. It's because you form the most stable radical. When we do hydrohalogenation, so that's HBr across a double bond, the proton adds first to make the most stable carbocation, and that's why we get Markovnikov addition with that. We also looked at allylic bromination with NBS, so you might remember N-bromosuccinimide, this little guy, so NBS, in case you ever see it, again, you want to have it in your mind. You want to know what the molecule looks like. This is N-bromosuccinimide. And then we also looked at the bromination of alkanes, and this is something that's going to come up a lot in chapter 11. Anytime I give you an alkane as a starting material, the first step is just going to be treat it with bromine, functionalize it, make an alkyl halide, and then we're going to decide what to do with it after that.